Hello, everyone. I welcome you all to the last session of this semester's Kent Seminar Series. Today, we are delighted to have Mr. Reilly from AECOM with us. Mr. Reilly serves as an Associate Vice President and Electrical Senior Manager in Illinois for AECOM's Traffic, ITS, and Electrical Division. He specializes in electrical, ITS, and EV charging infrastructure design and has many years of experience. He has provided significant electrical designs for various DOTs, airports, railroads, and other agencies across the country. He holds a bachelor's degree in electrical engineering and is a professional engineer in 13 states. Everyone, please join me in welcoming Mr. Reilly.
Thank you for the kind introduction here. So today I'll be presenting to you about dynamic wireless power transfer, or DWPT, EV charging pilot projects that AECOM is working on. Can you still hear me okay?
We can hear you well.
Okay, good. Just making sure before I keep going here. So for the agenda here, some things that I want to cover today about the pilot projects that we're working on. And a snapshot view here, you can see of the roadway for US 52 for one of the pilot projects with Indiana DOT that we're working on. So as you can see, it's concrete roadway, 2 lanes divided each way. But beyond that, you don't see a whole lot else out there on the road that might tip you off that there's something's unique taking place here other than the concrete pavement itself. So keep that in mind here as we move along. So just to give you a little bit of background on dynamic wireless power transfer, what it is, as you're probably well aware now through these seminar series, but it's basically transmitting power from a transmitter to a receiver through time varying magnetic fields, much akin to the way that your cell phone charges wirelessly at home, just on a much larger scale. So whereas your cell phone charger is typically in the 15-watt type of range, these dynamic wireless power transfer systems for vehicles are aiming more in the 200 kW range, in that level 3 type of charging range. But basically sending power wirelessly from the roadway up to a vehicle, that a vehicle has a receiver built into it. So why does it matter? And some of the use cases for this type of technology for wireless charging is highway charging for light and heavy duty vehicles, especially with heavy duty vehicles, being able to keep them en route and driving for longer distances without having to stop. And then wireless in-route opportunity charging too for buses, fleet vehicles, things like that, that might make key stops along their route and have an opportunity if they're sitting to charge while sitting there momentarily or for a short period of time. And in fleet charging as well too, if you have a fleet of vehicles, static charging overnight at a facility or garage, whatever the case might be. And then also in the future here with autonomous vehicles, you can imagine autonomous vehicles running around, picking up passengers, making different routes. And if there's nobody driving the vehicle, there's also means there's nobody to plug in the vehicle to charge it. So if the vehicle could park autonomously over a charging pad wirelessly, it could enable recharging of that vehicle. And then also bidirectional grid power sharing too, as these vehicles have the potential to reshare power back into the grid when they're not being used. And with any technology, interoperability is a key factor to enabling widespread adoption and usage. So SAE has some standards for wireless power transfer from light duty vehicles all the way up to this dynamic wireless power transfer. So the one key standard we're looking for here is J29543. That's supposed to be released here in 2024. I don't believe last time I checked it's been released yet, but this will be the standard that will be written for this dynamic in motion power transfer instead of just static like the first 2 versions up at the top. So that'll really enable the industry to build more of these vehicles with that capability built in around a common standard. So for the pilot project that mainly be talking about today is with the Indiana DOT and Purdue University. So we've been working with them over the past year and a half almost on this project. So the purpose of this pilot here is basically to validate this dynamic wireless power transfer on a large scale, on an actual roadway, test the constructability, functionality, and capabilities of it to charge a moving vehicle driving down the highway. So this, like I said, it's a 2-lane divided highway on US 52 in West Lafayette. We installed the system over about a 1/4 mile of roadway right next to the INDOT subdistrict office there. You can see some of the pictures inset here with the parking lot and the facility right adjacent to the highway for convenience. And you can see some photos from the groundbreaking ceremony they had. And then also a little inset photo in the lower right corner. You can see some of the installation taking place. You can see these vaults being installed in the side slope of the roadway. So construction is well underway right now. The pilot, it's centered around a Cummins Class 8 truck for this evaluation. So the overall goal of the pilot is to see, can we get a heavy duty truck to maintain a state of charge essentially over a course period and distance. Basically, could you have this type of system installed for a 1/4 mile every, say, 10 miles to keep a truck at a status charge and enable it to keep moving down the highway and make long haul deliveries or more local routes, whatever the case might be, but just to keep it moving where it wouldn't have to stop to charge. The goal of these chargers is to deliver up to 230 kilowatts per pad, so pretty high energy, like I mentioned earlier. The transmitter design is a 3-phase design with 3 separate phases of wires in the transmitter coils and also in the receiver coils as well to help balance out different loads there. And then you can see some pictures here of the truck for the evaluation, and then a kind of overview picture of how the system gets fed down the roadway. So you have a controlled trailer that's going to be rented. You got a rental generator that they're going to rent to supply power, since it is a pilot. They didn't want to get a more permanent utility service. And then a transformer rectifier to send power out to the roadway from that generator. And then the system's using DC and AC power distribution up and down the roadway to these vaults with power electronics inside. So we're using DC power distribution for the main power to these electronics and to the transmitters. And then also AC 120 volt power distribution for some of the lower voltage control electronics that are inside that vault. We also have Cat 6 and multimode fiber communications up and down the roadway. And you might ask why we have both. Well, we have the multimode fiber is being used more specifically for a high frequency clock synchronization between all these transmitters inside these vaults, these inverters, to be able to track a vehicle moving fast down the highway, to keep up and monitor where it's at and synchronize the charging between adjacent coils essentially. And then we have Cat 6 communications too for normal status monitoring, health monitoring of these electronics and different sensor parameters, things like that, that we can monitor. So where we're at right now in the project schedule, we've been through bidding phase this last fall. You can see a picture here from the pre-bid meeting that Purdue brought out a sample coil on a trailer so the contractors could see and feel what it looks like and what they're being expected to install. And then right now we're in the construction phase here. Construction is mostly done right now, but then in the spring, they're going to follow back up and put in some of the charging inverters and electronics in the vaults due to the longer lead time that some of those materials take to procure and fabricate since they're all custom. And then after construction is done in the spring, that's when it'll be handed over from the contractor to INDOT and Purdue for testing phase. So, and then you can see some pictures here of the contractors installing the coils and then placing the concrete overlay over top of them. So this was definitely a challenging project with no set standards for such an installation in the INDOT's standard repertoire of highway drawings. So we had to come up with a custom design for pretty much everything. The roadway that they chose was very specifically selected due to its location, and it's also pretty recently constructed concrete pavement. So the pavement was all in good shape. It's all concrete pavement. So they wanted to mill out a trench in the pavement to drop the coils in, and then cut a 4-foot hole in the center of that trench to enable the conduit to be directional bored to the center of the lane. So there was no saw cutting through the concrete to get conduit out to there. No disturbance to the shoulder either. They were able to directional bore from the side slope out and miss the under drain as well. That was another concern that we had to address in the contract documents. And then in the side slope there, that's where we designed these specialized vaults to hold the power electronics and receive all the cabling up and down the roadway, and then also from the lanes. And then you can see here, each roadway panel was 15 foot long, and they wanted to put a slot in the roadway panel to fit the coils in place, and without disturbing the dowels in the adjacent concrete panel sections. So we had a gap there between them to make sure we weren't damaging the concrete. And a lot of finite element analysis went into the concrete analysis to make sure that all this work wasn't going to damage the roadway and limit any potential for cracking. That was another concern NDOT had early on. As part of the design here, we had to include these AC to DC transformer rectifier units. So it's basically a big cabinet you see on the left-hand side here. It has a transformer in there and AC to DC rectifier to take power, AC 3-phase power from the generator and turn it to DC power to send out to the lanes. It even had to have an emergency stop button on the side of the cabinet to ease any concerns from the fire department too. If there was a incident on the roadway, a crash or fire, things like that, they wanted to be able to make sure they had a way to shut off power to the roadway for their safety as well. We also had to design special disconnect switches and junction boxes on this rack here, you can see, to be able to connect up the incoming power for the 120 volts AC, and then also disconnect the power running out to the roadway as well. Have a convenient place for that and protection for those circuits. And then the smaller box on the rack there was for communications cabling to run to the future adjacent control trailer. And then with all these electronics, they had to go right close to the lanes to power the transmitters. We had to design these special polymer concrete vaults to hold these inverter enclosures, which we'll see pictures of later. But basically, these polymer vaults are about 6.5 by 8 feet wide. So pretty big, double lid design, heavy loading requirements there to make sure if any vehicles did drive over them, the lid could still survive without any issues. But basically, these vaults are used to send all the power cabling in and out between the adjacent vaults and then out to the lanes with the specialized wires running to the transmitters. And with the power distribution, we had to use specialized DLO cables for the design. The design was based around 750 volts DC power distribution up and down the roadway. So what that means is any of your normal standard 600 volt rated cables and disconnects and materials like that wouldn't work for this type of application. So we had to we had to specify special DLO cables, which are rated for 2000 volts, but they're also very flexible too with the fine stranding here. You can see in the image in the lower left corner. So what that does is it enables them to be flexible, bend easily inside these vaults, whereas they were pretty big cables too. They were like 444 kc mil. But if that was a regular 600 volt style power cable, it would be very difficult to bend in a vault like that. And then we had special Cat 6 on multimode fiber cables as well for communications. It could be outdoor rated and survive underground. And then that's specialized Litz wire for these embedded coils. Here you can see some pictures of this really finely stranded Litz wire and rolled up Litz wire coils there being ready to be placed. So the contractors had to arrange them in special patterns and not have any splices back to the vault. Even the wires had to be specially wound and twisted in the bundle running back to the vault and minimize interference with each other. So they were able to kind of prefabricate these coil patterns offsite, roll them up on these special PVC fiberglass ladders and bring it out to the site, install it to fish the wires through the conduit back to the vault and simplify the installation in the field. And then for these inverters that live in those vaults, they're sort of the main heart of the system, converting that DC power to three-phase AC output. So what they do is create a very high frequency AC output to enable the charging from the coil, transmitter coil to the receiver coil. I think it was about 75,000 hertz. And these had to be IP68 rated submersible enclosures. So you can see they have a lot of screws on there, a lot of special cable glands, make sure it's all sealed watertight, even heat sink fins on the bottom to get the heat out of the enclosure. They also have a controller inside with a 4-port Ethernet switch built in for communications. And then on the lower picture there, you can see on the bottom table is the transmitter coil that is in the pavement essentially. And then above that is the receiver coil that would be built into a vehicle. So these have specialized capacitors and inductors to tune these coils and make some adjustments in the field as they're doing their testing. So pretty much this set is, you have a set of inverter and transmitter and receiver. Well, not necessarily a receiver because that's in the vehicle, but one set per coil or per roadway panel. So pretty much each 15-foot roadway panel has an inverter and a transmitter to power it. So each vault has 2 of these inverters in it. So each vault powers 2 roadway panels essentially. Another tricky thing with this project we had to figure out was acceptance testing. So the INDOT contractor is building the system and they're supplying a lot of the materials and equipment there. But then there's also other equipment that's going to be provided by others. And then the whole system has to be tested and turned over from the contractor to INDOT. So how do we figure out that? How do we go about that process and prove that the system works? So we had to come up with acceptance test plans and requirements for that so that the contractor could get paid at the end of the day for the work they did and turn over a quality product that was going to work for INDOT and Purdue for long-term testing here. Because without that, you would be difficult to prove that the whole system worked without all the different components in place. So here you can see a photo of them doing some Megger testing of the Litz wire coils in the pavement to prove the cables are intact and not damaged. We also had to review a lot of the shop drawings for these products as well. So some were more challenging than others for custom products, but we had to work through that and work through any of the issues that we saw and changes that may come along the way. But a lot of the different products, some turned out exactly how we specified and planned, and others were more unique. So it was a good process to go through. And then also helped out with some field inspection as well, reviewing the installation and checking for things, making sure the installation matched the plans and design intent. And then what does this mean overall for sort of the future of wirelessly charged vehicles? Basically, if we could have wireless charging of the vehicles, that would enable in-route recharging and then also potentially lighter vehicles. So if you could recharge along the way with trucks or light-duty vehicles, you could reduce the battery size in those vehicles, which would enable lighter vehicles, more fuel efficient or energy efficient vehicles there if you don't have so much weight to drag around. And then also safety considerations too. You know, with EVs generally being heavier than gas vehicles, you know, if any weight you can strip out of them makes them better or safer. You see some either crash test videos or fire situations that might happen. You know, if you could strip out the battery weight, the battery energy, lower all that down, could lead to safer vehicles and take out some of the materials needed for those vehicles too. And then also it enables autonomous vehicles too in the future, where if you didn't have to park and charge at a plug-in station, these autonomous vehicles could keep driving along their routes, be it buses, trucks, whatever the case might be, taxis, things like that. They could operate more autonomously without having a physical plug-in power connection. Some of the other pilot projects that we're working on here, we're working on one for Michigan DOT, where the owners are up on this project, doing a dynamic wireless power transfer pilot for a few streets in Detroit. So here you can see some photos from the 14th Street installation and 15th Street installation too, where they're going to wirelessly charge some Ford Transit vans for shuttles for I think Ford down there. And then they're also hoping to install a longer section of this on US 12 or Michigan Avenue there in Detroit too in the near future to keep expanding on the pilot project and testing some more use cases and applications there. I should say that pilot was based on the Electrion design as well. Another project we're working on is with Florida DOT for their SunTrax test facility. So this test facility down there has a lot of different capabilities for different vehicle testing, connected vehicle testing, things like that. But they wanted to do a dynamic wireless pilot project as well. So we're working on that, we put together RFP for them to put a project out for bids to do this design and work and installation. So that's underway. It's largely based on Electrion design for this system as well. So that's in the works here. They were hoping to issue that RFP this year as well. And another one close to home here is the IAC test track that AECOM's been working on. So we've been working on the overall site design for the entire track, as well as some of the wireless and pavement charging for it. So the test track has a whole host of features for connected autonomous vehicles. But one of the aspects of it is inductive wireless charging and also energy harvesting that the university wants to test. So this test system, not completely specified yet, but it's based around the INRIX design. So we'll see as additional funding becomes available for the project and we move forward, even forward in design here. We're at roughly a 90% stage with this project here in design. But as we move forward, we'll continue refining the design and implementation. And then another project that we're working on is with Nebraska DOT for I-80. This project, they want to do in-road charging and do a interstate dynamic wireless power transfer pilot. So on I-80, they're going to widen the roadway west of Lincoln, Nebraska to 6 lanes. So here you can see a picture of the roadway cross section. I believe they're going to fill in the inner 2 lanes to make it 6 lanes wide, probably do a closed median there. But they wanted to do wireless power transfer pilot here. So we'll be working with them to define requirements, establish design for the system, as well as test plans, integration, things like that as well, to be able to test heavy duty charging for the interstate applications. As you can imagine, I-80 has a high volume of truck traffic, so we're working with trucking companies as well to gain interest and traction with them for this pilot. So with that, that's the end of my presentation. I can open it up to questions.
Thank you so much for the nice presentation. We can have questions now. Yes, Johan.
Hi, Thank you so much for sharing these insights with us. I would like to ask you a bit more details about your acceptance protocol because this is a very new technology. So I'm not sure how rigorous those protocols are so far, or how do you find them? Because I think it's a really complicated thing to prove that this can work over long periods of time, with the restrictions of time that you sometimes have to deliver a project.
Yeah, it's very challenging to figure that out. Working closely with the different stakeholders and technology providers to come up with a test plan and prove that the system can work. So you largely have to validate that energy is actually being transferred. So we've been working with INDOT and Purdue on that. Purdue's been doing a lot of testing in their labs as well, testing if the system can transfer power to a load bank in their lab. So basically they have those two coils set up. I go back to the picture here. They have these two coils set up on the tables there, and they can move the tables in relation to each other. And then they have load banks off to the side where they can shed off the power transfer as heat loss, essentially. So they're testing that there in the lab to kind of validate that it can transfer power and perform as needed with the actual inverter electronics being supplied to the project. So they've done this in the past prior to the project itself, but now with these actual inverters for the specific project being fabricated and able to be tested, that's what they're doing now.
Thank you so much.
You have, okay. Yeah.
Hi, Greg. Can you please elaborate on the FEM analysis that was done to make sure that the pavement wasn't going to crack whenever these were embedded?
Sure. So INDOT's research group did finite element analysis for the pavement because they were concerned with these slots being cut in the pavement and holes being cored. They didn't want that to create long-term failures for this pavement. Just because the pilot project, they wanted to validate it and make sure that whatever we do here will be successful and doesn't create long-term issues here for this site, or then also moving forward in the future for other sites too. So there was kind of more crossing the T's and dotting the I's to make sure that everything was accounted for. But yeah, they ran analysis there and different ways to cut the pavement here, trying to minimize any saw cuts in the pavement. That was one primary concern. They didn't want us to cut the pavement from the shoulder. At first, we thought of that idea too, to bring the conduit out there, because obviously somehow you have to get conduit from the roadside to the center of the lane. So how do you do that without saw cutting through the pavement? So we did that through the design here. It was 10-inch pavement there. So we had to core a 4-foot hole through that in the center for the cables to come through. But yeah, they ran the analysis to help make sure that the pavement was going to survive.
Thank you.
I have a couple of questions. The first one is regarding the semi-truck that's being planned to use for the wireless charging. So the first one is, what's the battery size, and was a standard electric truck converted or modified for wireless charging? And the second question is regarding the Michigan DOT's pilot project, in which probably the technology supplier was Electrion. So I believe in that project, it was in asphalt concrete. So what protocols were followed to embed the wireless charging pads in asphalt concrete? Like, what was the design procedure? Thank you.
Yeah. So for the Cummins truck, don't have a great deal of details about that, but it's a electric truck that Cummins is providing for the pilot, essentially. So they're providing this electric truck. I've seen it in person. It's got batteries underneath it. It's got no engine. Underneath the hood is more of the motors and electronics. So which is kind of funny to see for a gigantic truck like that. Not a whole lot under the hood, but it's going to have a wireless receiver pad underneath the vehicle. So basically, Purdue's working on sort of designing this receiver module essentially that they can bolt up to the bottom of the truck, and then that'll tap into the truck's charging electronics. It's kind of like Cummins supplies a truck, and then anything you do to it, it's out of warranty essentially, kind of deal. But then the second question there for the Michigan DOT project, yeah, that was based on Electrion. I believe that one, they used a lot of asphalt roadways for that one. This is more downtown Detroit. Probably didn't have a lot of concrete pavement there, but they put these coils down over the asphalt base layer, and then they carefully rolled over them with a smaller, like 4-inch lift of asphalt over top of that. So the coils are shallow still as well, but they were able to put that over the top of them, and they had to figure out good times to do it, good temperatures to do it at, and not vibrate the rollers as well over the coils because they didn't want to damage them. So a lot of little different things and considerations that had to be made versus a standard asphalt roadway job.
Okay, thank you. We have a question in the chat. I guess it's Professor Thompson. Does the system have to be continuous, or what is the minimum length?
It doesn't have to be continuous. So with the Purdue INDOT pilot, the goal was to install this over about a 1/4 mile of roadway. And then the theory would be if you could do this on the interstate, on I-65 or other interstates across the country, you could install this every 10 miles, say. And then as a truck travels over these coils, it would boost the power up, and then it slowly decrease power and consume energy from the batteries over the next 9 miles. And then it would get to the next system to charge up, and it would boost back up and then keep drawing down. So that's kind of the goal of it, is just to kind of keep a vehicle at a certain state of charge.
Thank you for the very nice presentation. When wireless charging came out in the phones, I think still as recently, they had some overheating problems, and I think at some point some of them catch fire. So when it comes to these trucks, is the manufacturer doing the wireless pad underneath, or is it the research team, or who's retrofitting the wireless charging technology there?
So it's a little tough to hear. Who's testing the wireless charging technology?
Who's retrofitting the wireless pad underneath the truck? Is it the manufacturer, or is it a research group, or some third-party company?
I think it'll be probably a combination of the research group and Cummins. They'll probably work hand in hand to try and figure that out, because obviously Cummins knows their vehicle very well and how to actually connect that up, since it is fairly new to an electric semi truck like that. So yeah, they should work together to figure out exactly how to connect it up. And like you said, with heat and catching fire, you're saying the vehicle might catch fire. They have had those discussions there. Heat is a concern with the charging electronics, and shedding heat from that under the vehicle, since there's really not a whole lot of airflow down there. So that's definitely something that needs to be considered.
Thank you for the presentation. I just have a very basic, quick question. It's about how do you activate the charging? Like, is it gonna be on the whole time, or is it, for example, activated when some vehicles move? And also, if that's the case, like, what if some vehicle doesn't have the receiver coil? Are you still gonna try to charge it? Something like that.
Yeah, so for the pilot, it'll just be activated when they're doing testing. So normally it won't be energized, it'll be off. Because for this pilot, they'll have to run the generator too, so they'll want to make sure they're having a purpose for running that and powering the system up. But in a long-term application, there's a two-way communication that happens between the system in the road and the vehicle as part of that SAE standard. So the vehicle has to kind of communicate to the roadway and say, hey, I'm here. I want to charge to enable the charging to the vehicle. And then long term too, you could see this, how do you monetize this? How do you make it sustainable for funding? And then you'd have to have that communication mechanism in place to be able to charge for the charging. So much like a toll transponder in your vehicle, the system like that would know, hey, this driver has paid for this subscription or this service or wants to pay for charging, and it could talk to the vehicle and know that, okay, this is the vehicle's account information, credit card information, whatever, to be able to pay for the use of the energy.
Thank you.
We have a question. Is it possible?
Yeah, go ahead.
My question is, does the system have a durability? Is the design system about the snow load, the load of the overload, the capacity of the wind, or sometimes the temperature of the earth because it is on the floor? So in addition, overloading, if the car is passed or vehicle or others, how in a year, how many vehicles, how many loads overloaded? Is it oriented? The design is oriented with that. So the design, when it is oriented, for how many years it is oriented. In addition, the durability is may be answered in that case. It is including with the material capacity.
Yeah, I think it's overall these systems are designed for durability. With technology and the roadway, it's a challenging topic because technology evolves so much faster than the civil infrastructure does. But if these systems have a 10-year lifespan, give or take, if that's a common approach that the industry wants to take for them, designing that type of durability in, if the roadway, they want to test it to make sure that the roadway can survive and not receive cracking, things like that over a long time. With the snow plows as well too. These pilots are kind of set up to enable plowing as regular operation with no impact. There's no raised portion of it that might impact the snow plows. So all that's kind of being taken into consideration. For the INDOT pilot, they used this special polymer concrete material, almost like not quite like a two-part epoxy, but of a special cement mixture that they have used before on bridge approach pavements. So INDOT's used that before with success. So they wanted to use that here as well, and it's more flowable than regular concrete is. So it can get in and around these coils and under there to support them and avoid any voids in the concrete there.
I want to know, it is not I apologize if it is included with the preliminary observation and about the soil mechanics, if there is a pressure, and also the design system of the load overloading, how many vehicles go every year, and if there is a snow, if everything is oriented, it is okay. That is what I want to know. Thank you.
Sure. Yeah, for this pilot, it's oriented around one test vehicle. Depending how many vehicles you wanted to power at the same time, you are sort of limited by the amount of power coming into the this quarter mile of roadway. So this system was set up to be able to charge, 230 kilowatts to one vehicle essentially. Now, if you had multiple vehicles, they would have to share that power. But for this one, they just have the one vehicle to test.
Thank you, Greg, for the interesting presentation. I have two quick questions.
Any other questions?
Yes, can you hear me?
Yeah, I can hear you.
Thank you for the interesting presentation. I have two quick questions. One of them is, if you don't mind, can you touch bases on rough estimation of the efficiency comparison between the different technologies? You mentioned like NRIGs, and then you have the other technology. And I wonder, question two, in this slide specifically, is this technique continuous or separate? Because we can clearly see you're bringing the coil down the right of way to the fault boxes, and then they're coming back again. Maybe I missed that in the presentation. That's all.
Yeah, so the system wouldn't be continuous. It's for this system, these coils are installed in each 15-foot concrete roadway panel, and then covered about a quarter mile total of roadway. So then there would be a gap in that, from that quarter mile of roadway to the next charging system, roughly 10 miles away if it was a highway application. And what was the first part of your question? I missed that part.
I noticed you mentioned several pilot projects and they're different technology, but maybe I missed it in the presentation. The efficiency of this power.
Oh, the efficiency. Yeah. I think they're hoping for above 90% efficiency, maybe 95, somewhere in there.
90.
95%, give or take. I think I'd have to look up the exact number again, but
These efficiency are based on your assumptions, which is like class 8 and also traffic. If that's
yeah, I think it's based on their tests so far in their labs. At least for Purdue, the other manufacturers, you'd have to discuss the specifics and efficiencies with them. What that is particular for Electron or NRIX.
Do you have any more questions in the room? If not, thank you so much, Mr. Reilly, for joining us today and presenting. Everyone.
Sure. Thanks, everyone. Great to present to you today. Look forward to working with you in the future.
Yes, for sure. Thank you so much.
Okay, thank you.
Yeah. Oh, no, unmute. I just have an announcement for the students who are registered